Okay, good afternoon, calculus students. This is Mr. Kong. I'm going to talk to you a little bit more about the second derivative and how we can use it. All right. On our last meeting, we talked about how we can use the second derivative to discuss the concavity of a function over a particular interval. We also talked about using the second derivative to help me find where the concavity changes. At what point does my concavity change? In other words, a point of inflection. Well, let's take a look at how we can apply that to a problem. Ladies and gentlemen, I want to show you how we can use the second derivative to find points of inflection and the concavity on an interval, right? Let's take a look at one of the problems out of your homework. These were the directions. In exercise 13 to 34, find the point of inflection and discuss the concavity of the graph of the function. Well, we know that number 17 is certainly inside of the interval of 13 to 34, so this is a problem that we should do. So let's take a look at this. All right, so I've got the function f of x equals x times x minus 4 to the third. Again, I want to find the points of inflection and the concavity. Well, before we do that, let's take a look at physically what this graph looks like. I took the liberty of going ahead and typing this function in. As you can see, I've typed this x times x minus 4 to the third into the graphic calculator. This is what the graph looks like. Okay? So this is the graph of that function. So I'm going to pull this out, and we're going to take a examine this, right? So let's take a look at this. I'm looking for the concavity of this guy and where the concavity changes, right? Well, if you think about this, as I follow along, as I take this point, as I trace this curve, I know that right in here, this looks like it's concave up, correct? All right. Here it looks like it's concave down. Here again, it looks like it's concave up. Agreed? Right? Well, I want to talk about on what interval is this function concave up, on what interval is it concave down, and what interval is it concave up again. Well, to determine that, I need to find where the concavity changes. In other words, I need to find a point of inflection. Well, I think that, again, we talked about this in the last class. It seems like the concavity on the left, actually, let me draw this point again, might change somewhere around, I think Brooke was the one shouting at me, change it, go. Maybe right here it's still concave up, but maybe right in here it changes concavity. So I'm thinking that I've got a point of inflection where my concavity changes somewhere at about 2 point something, maybe 2.5. All right? It looks like I also have another point of concavity right there on the x-axis. Doesn't it look like the concavity changes right there at 4? Right? So I'm guessing that my concavity is going to be up to the left of about 2.5. It's going to be down between 2.5 and 4, and it's going to be up again to the right of 4. Right? Well, to actually find out what's going on, I need to apply my calculus. So the first thing is I actually want to find these actual x values for my points of inflection. Right? Well, again, to do that, we need to find the second derivative. So let's do this. So let's see, if I've got f of x equals x quantity x minus 4 cubed, I know that f prime of x would equal, that's a little bit of my friend the product rule, so the derivative of the first times the second plus the derivative of the second times the first. Agreed? Now from here, I can try and take the second derivative as is, or I can try and simplify this the expression on the right side of the derivative before I move forward. So the first thing I'm going to do is I'm going to try and simplify this. Let's see, I know that I can factor out an x minus 4 to the second power from both this term and this term. If I do that, I get, let's see here, an x minus 4 plus 3x. Okay? Well, that becomes f prime of x then would equal x minus 4 squared times, well, golly, I think that just becomes, isn't it just 4x minus 4, right? All right, and I think it's going to be much easier to take the derivative of this expression on the right than it would have the initial derivative before I simplified. So now let me go ahead and take that derivative of the derivative, in other words, the second derivative. Well, I think that would be a little bit of, again, I got the product rule here. So derivative of the first would be this times the second plus the derivative of the second times the first. Agreed? Okay? So this is my second derivative. Now again, let's try and clean this up a little bit. Let's see what I can do here. I think again I can factor out an x minus 4 from the two terms. So if I take out an x minus 4 from this term here and this term here, I would be left with, let's see, 2 quantity 4x minus 4 plus 4 quantity x minus 4. Okay? Simplifying inside the brackets, I get, let's see, 8x minus 8 plus 4x minus 16, x minus 4, which yields simply, let's see here, I believe that's 12x minus 24. Okay? So that's what the second derivative equals, right? All right? All right, now, again, to find the points of inflection, we know that the points of inflection occur when the second derivative is set equal to 0. So setting this expression right here equal to 0, I get 0 equals x minus 4 times 12x minus 24, right? Well, what do I get? I get x minus 4. This is already in factor form, so I get x minus 4 equals 0, or 12x minus 24 equals 0. So wouldn't x equal 4? And x equals 2. So it looks like my points of inflection are at x equals 2 and at x equals 4, right? Okay? Well, let's see if that fits with what we were saying with the graph before. At x equals 2, let me erase all this mess here. It says here that x equals 2. This is actually where that point of inflection would be. And at x equals 4, and I think we had actually conjectured that it would be at 4. Comma 0, right? So those points of inflection, they make sense graphically on why those will be the points of inflection. Now, how do I, if I didn't have the graph, I know that to the left of this value of 2, I know that this is concave up, right? Between 2 and 4, this is concave down. This is opening downward. And to the right of 4, this is going to be concave up because, well, it's opening upwards, right? But mathematically, calculus-wise, how can I show that this is concave up, concave down, and concave up again? Well, again, I know that at x equals 4 and x equals 2, I know that that second derivative is equal to 0, right? Well, if I made a sign chart for my second derivative, right, I would get something that looks like this. I know at 2 and at 4, those critical values for the second derivative, that's where my points of inflection are. So what I need to do is test a number in this region here. I need to test that in the second derivative. Again, don't forget the second derivative is the derivative of the derivative, which means it tells me how much my derivative or slope of my function is changing as my x changes. Well, again, going up to this picture, we said, oh gosh, it looks like my slope is really negative, but it's slowly becoming a smaller negative number, or it's getting less negative, less negative, less negative. At this point, the slope is 0, and then my slope is positive. So it seems like my derivative is changing in a positive way. So that means that the change in my first derivative, in other words, the second derivative, that second derivative should yield a positive number here. My guess is that the f double prime, or my second derivative, my guess is that it would be more than 0, or positive on this side of 2. So how would I know? Well, couldn't I just pick a test number like 0? I'm going to put 0, and I'm going to actually put it in to the second derivative and see what I get. All right. Well, so going up to the second derivative, if I go f double prime at 0, that would be, let's see, 0 minus 4 times 12 times 0 minus 24. Oh gosh, I think that would be negative 4 times negative 24, which is equal to some positive number. I don't really care what the number is, 96 or whatever. I don't really care. I just care that it's positive. Because that verifies that, yeah, the slope was changing in a positive way. My second derivative is positive, so I know that this interval from negative infinity, sorry about my penmanship, from negative infinity to 2, this interval right here is concave up. All right? Now again, I think we said that from between negative 2 and between positive 2 and 4, it would be concave down. So let's pick a number that's in the interval here and test that in the second derivative. So let's pick nice and tidy 3. So plugging 3 in to the second derivative, I would get 3 minus 4 times 12 times 3 minus 24, which would give me negative 1 times, let's see, that would be 36 minus 24 is 12, which would be negative. And I really don't care what the number is. I'll go ahead and write negative 12. But again, that must mean that my derivative is actually starting to slow down. The slope is starting to slow down and start getting closer to becoming a negative number again. Okay? So I know that between 2 and 4, I know on this interval, I'm concave down. And then lastly, between 4 and infinity on this side, right? On this side of 4. Again, picture-wise, it looks like it should be concave up, but just to make sure, let's take a number in this interval after 4, and let's see what we get. So let's pick a nice and tidy number like 5.11. Let's test 5.11 since it's an easy number to do with our math. Plugging that in, I would get the second derivative of 5.11 would equal 5.11 minus 4 times 12 times 5.11 minus 24. Well, that would equal 1.11 times, well, gosh, that's 36 points, 37. Well, I know that's going to be a positive number. And let's see, what's a positive 1.11 times a positive? It's a positive. Again, do I really care about the number, or do I just care that the second derivative is positive? Yeah? So I know that to the right of 4, my second derivative was positive, so I know that on the interval of 4 to infinity, again, I must be concave up. And so that's how I found my critical values and how I find the concavity of the intervals that are created on each side of the points of inflection. Now, to actually find the points of inflection, does it make sense? I've got the x value for my point of inflection. Well, to find a y value for that point, don't I have to take this guy and plug it all the way back up into the original function here and here to get the y value? All right? So if I do that, if I plug the point of, to get the point of inflection, I'm going to plug f at 2 and get 2 quantity x minus old memory x minus 4. I'm sorry, my bad. 2 times 2 minus 4 cubed to get the y value, which would give me, let's see here, that's negative 2 cubed is negative 8, so negative 16. So I know there's a point of inflection at 2 comma negative 16. Again, plugging 4 in now, again, because I know there's a point of inflection of 4, plugging in 4 into the original function, golly, I think that's an x-intercept, so I hope I get 0. So plugging in 4, I get 4 times 4 minus 4 cubed. Well, God, there it is. I know I get 0. So I know the other point of inflection is at 4 comma 0. Okay? And that's really, again, the purpose of the second derivative and to find points of inflection and concavity.